Hey everyone, welcome to the first lesson of calculus. In this lesson and in this unit, our focus is going to be on limits and continuity. We're also going to dive into the idea of average rate versus instantaneous rate, and the idea of secant lines versus tangent lines, and you're going to see how all of this wraps together as we go along. But for this unit, or for this lesson, our goal is to be able to determine the limit of a function by applying the properties of limits. Now, what is a limit? A limit, the idea of a limit is that it's a y value, essentially. First, remember that it's a y value, it's not an x value. A limit is what the graph of a function is approaching as x approaches a certain value. What is the y value approaching? Now, if we're looking at, and so if you look at the definition, it says a value L that a function approaches as the input value gets closer to its destination C. The bottom line is L stands for limit, and that is a y value, and C is the constant or the numeric value that the x value is approaching, okay? So we write it like this. We write limit as x approaches C of f of x equals L. And essentially what we're saying, as a particle moves along the path of a function, what does its y value get closer and closer to as its x value approaches a certain value? So just reading the statement, it says the limit as x approaches C of f of x equals L. So as x gets closer and closer to a specific value, the function approaches a certain y value. And so you can see in the picture, C is what we're trying to approach in terms of x. As we move our finger along the curve from left to right, you can see that the function is approaching, as we get closer and closer to C, the function is approaching a height that is identified as L. And then on the other side, if we approach it from right to left, we are also approaching L, okay? Now, the reason that this is important, some might say, well, that's obvious, that's like a duh statement. But the reason that this is important is because we might have functions that are what's called discontinuous. And so we're going to get more into continuity and discontinuity later on. But if I have, let's say, a function that looks something like this, and I have a hole here, there's a missing piece. Now, you learn this in Algebra 2 or Math 3, analysis, something along that line, that there's this idea that there can be a removable discontinuity, a hole where we are trying to look for a value. So if I were to say this is like 5, we would say that f of 5 does not exist, okay? Because there is no y value that is associated with that x value. But we see that as we move closer and closer in the x direction towards 5 from both sides, that they are approaching a value. They're getting closer and closer to a number. Now, they don't actually touch that number, but they're getting closer and closer and closer to it, infinitely close to it, we would say. So let's say that this is 2. F of 5 does not equal 2. F of 5 does not exist because there's a hole there. But we would say the limit as x approaches 5 of f of x is 2. So this is saying we are getting closer and closer to the value of 2 as x gets closer and closer to 5, but the graph shows that the actual value doesn't exist there. Okay, we'll see the application and the purpose of that later on, but that's the idea. Okay, that's the idea of a limit. Now, as long as a function is continuous, then we can say that these two things are going to be the same thing if the function is continuous. So let me fill this hole in here. Now this is a continuous function. And so since we know that the limit as x approaches 5 of the function is 2, and the function is continuous at that point, we can also conclude that f of 5 is 2. Okay? what this does for us, it actually makes it really easy to determine limits. This sounds like a really complicated idea, but analytically it becomes very easy. If the function is continuous, it's continuous. If it's continuous, then we can simply say, okay, I need to figure out this limit. What is it? Well, we know that it's the same as the function's value at that point, because it's a continuous function. And since we know that f of 5 is 2, we can conclude that the limit is 2. In other words, analytically, in order to find a limit, all we have to do is plug in the x value to the function and get an answer. That's all we have to do. It's the same as saying, what's f of 5? This only works if the function's continuous, so we have to be careful of that. We have to check to see if the function's continuous, but all we have to do is substitute. Now, in this example here, we have f of x equals x squared plus x minus 4. Okay? So this is simple. If I'm looking for the limit as x approaches 1 of f of x, well, we would ask ourselves first, is this function continuous? Well, this is a parabola. It's continuous. It's continuous at every point, so we don't have to worry about whether there's any holes in the way. So all I have to do is figure out what f of 1 is, which means all I have to do is plug in 1 in order to get an answer. So that's going to be negative 2 there, and so that is our answer. Okay? So as long as the function's continuous, all we have to do is substitute. And you can notice the notation here. I wrote it out in words. What is the limit of f of x as x approaches 1? This is how we say that. The limit of f of x as x approaches 1, or the limit as x approaches 1 of f of x. But the bottom line is, all we have to do is substitute, because this is a continuous function. A quadratic is continuous. Again, we'll get more into that into the future. So we end up with negative 2 there. Let's go ahead and take a look at another problem here, practice problem. So if you find it beneficial to pause the video and try this on your own, and then pushing play, that's fine, you can do that. But I'm going to go ahead and go over this. We are looking for the limit as x approaches negative 3 of g of x. That's the question. Well, let's look at g of x. G of x is equal to x plus 6 over x minus 5x squared. Okay, so this can be either a really easy problem or a more in-depth problem. Remember, all we have to do is substitute into the function if the function is continuous at that point. So we look at this function, we say, okay, is this function continuous at negative 3? Well, we notice we have a problem here because we are dividing by x. And normally that's not an issue. We can divide by any number we want except 0. We're not allowed to divide by 0. So if x is 0, then we have a point of discontinuity of this function, okay, because we're dividing by 0 there. So we couldn't substitute to find a limit if we were looking for the limit as x approaches 0. But because we're looking at the limit as x approaches negative 3, well, this function is continuous at negative 3 because there is no problems mathematically with this. So all I have to do is substitute into this equation, into this function, to find the answer, because the function is continuous at the point that we're trying to find the limit. So we end up with 3 over negative 3 here. Remember your order of operations. I think it's funny but sad at the same time that calculus students tend to forget all about other math when they get to calculus. Make sure you're paying attention to good math practices here. So we end up with negative 46 as an answer for that. Let me double check to make sure I'm right. I don't want to give you false information here. So we end up with negative 46. So that is correct. All right, the limit as x approaches negative 3 of g of x is negative 46. All right, let's go ahead and take a look at an example here of a place where we might run into a problem. Here we have a function h of x, and it says that h of x is x cubed minus 1 over x minus 1. And we are looking for the limit as x approaches 1 of h of x. Now, normally we'd say, let's substitute. We can just substitute, plug in 1. Well, first of all, we notice that if I plug in 1, I'm going to get a 0 in the denominator. So that's a problem. But we always substitute. Even if we can recognize that there's going to be some sort of problem to begin with, we always substitute, because later on in future lessons, in future calculus, we're going to get to a rule that's going to help us determine limits really easy. But if we don't check substitution, we're going to make a mistake in those later concepts. So we need to make sure that we have good practice and good mathematical practices as we go along to make sure we're prepared for that. So we are going to just plug in 1. We're going to substitute. We always check substitution first, no matter what, even if we think that there's going to be a problem. Okay? Here, if we simplify this, we end up with 0 over 0. Now, I'll talk about it briefly here. We'll talk about it more in the future. But if I take any number, well, let me rephrase that. If I have a 0 on top and any number on the bottom where, we'll say where c is not 0, then what's the answer? What's 0 divided by c as long as c is not 0? Well, the answer is 0. 0 divided by any number is 0. Well, if I have any number divided by 0 where c is not 0, you go, c could be 0. We'll get to that in a second, okay? Any number divided by 0, we can't divide by 0. We say does not exist, okay? Now, we're talking about limits here, so we're actually talking about something other than basic math of something divided by 0. We're not actually dividing by 0 in the strictest sense when we're talking about limits. We're actually dividing by something that's really, really infinitely close to 0. So we're actually going to get an answer here of either plus or minus infinity. Again, we'll talk about that more in the future. Don't stress out about that. The point is this. The 0 in the numerator indicates that the answer should be 0. The 0 in the denominator indicates that the answer should be infinity. These two answers contradict each other. They don't make sense. They don't go together. They don't agree. And so 0 divided by 0, in terms of limits, we're not going to say, oh, that just does not exist. We don't know what this is, because the 0 on top says the answer should be 0, and the 0 on the bottom says the answer does not exist. This is actually referred to as indeterminate. Okay? In other words, if we get this kind of answer out, that means we don't have an answer. This is not an answer. This is indicating that there might be an answer, but we just don't know what it is yet. Okay? So if you substitute in and you get 0 over 0 out, then you know the answer, that's not an answer. That's not an acceptable answer. If you leave it there and just say, oh, it's indeterminate, that's not an answer. Indeterminate means, I don't know. This isn't enough information yet. Okay? So now we have to do something more in order to figure this out. Okay? Now, we're going to try substitution. We did that. Okay? And we got something called indeterminate. We got 0 over 0. H of 1 is 0 over 0. Does not exist if we're looking for h of 1, but if we're looking for the limit, we say it's indeterminate. Now, what are we going to do? Well, let's use a table to get an idea of what this looks like as we move closer. Okay? So here's the idea. Let me pull that back up. You're going to get your calculator out to make this a little bit quicker, and you're going to type the function x cubed minus 1 over x minus 1 into your y list, and we've talked about that in prior lessons, so make sure we know how to do this. Okay, we're going to type it into our y list. We're going to go to our table set, which is the green F4 here. We're going to hit the diamond, the green diamond, F4, and that brings up the table set. We need to scroll down until it says independent. We're going to scroll over to independent. You have the option of saying auto or ask. We want that to say ask, and then you're going to hit enter to save that. It's going to bring you back to your y list, and then now we're going to go to our actual table. So we're going to hit our green table, and some values might have popped up. Ignore those for right now. What we want to do here is create a table from the left and from the right to get an idea of what this function is approaching. Now we can look at a graph and see it, but we need to see it in terms of tables as well. So we are going to pick values that are approaching the value of 1 from the left. So maybe we'll start out at, I don't know, maybe we'll start out at 0, and and then we'll move closer to 1 from 0. So what's a number closer to 1 than 0? Well, maybe 0.5, half. Well, what's closer to 1? Maybe 0.1 is closer to 1. Sorry, I'm going backwards here. Maybe 0.9 is closer to 1. What's closer to 1 than 9? Well, maybe 0.99, right? So we're looking for values. We're trying to estimate the idea of what the function is approaching. As x gets closer and closer to 1, what is f of x approaching? Now, notice you don't have to be consistent. You don't want to be consistent in terms of the gaps between the two. This is a half apart. That's 0.4 apart. That's 0.09. That doesn't matter. You want it to get closer and closer and closer. The one thing you don't want to do is put a 1 there, because we already know the 1 doesn't produce an answer that is valuable. So we're going to go with our calculator. We're going to type in 0 into the x value, and we're going to get something out. We get 1 out. Then we're going to type in 0.5, and we're going to get 1.75 out. And then we're going to type in 0.9, so we end up with 2.71. And then we'll type in 0.99, and we end up with 2.9701. And then we'll type in the last one here. We get 2.997. Now we can keep going, but our calculator actually has a problem because it only stores digits, certain length of digits. So my guess is if you were to plug in something closer to that, it wouldn't be actually perfect answer. But we can see a trend here. We can see that from the left, as we get closer and closer to 1, do you see the y value getting closer and closer and closer to a specific value? Well, we can kind of see that it's getting closer and closer to 3. So we'll check from the right. We'll check from the right. Well, what are some values that we want to approach 1 with from the right? Well, maybe we'll start at 2, and we're going to go backwards now. Maybe we'll go to 1.5 and 1.1 and 1.01, right? And so on. Maybe 1.001, right? We're getting really, really close to 1. But again, if we plug in 1, we're going to get something that doesn't work. So we're just going to continue in our table. We're going to type in 2. 2, we get 7. And 1.5, we get 4.75. How about 1.1? We end up with 3.31. And 1.01, we end up with 3.0301. And we'll do one more, 1.001. We end up with 3.003. And so you can see that as x gets closer to 1 from the right-hand side, we are also approaching the value of 3. So the limit as x approaches 1 of h of x appears to be 3. It looks like it's going to be 3. That's good. Now, does this prove it? No, this is just kind of experimenting and seeing what it looks like is happening. This doesn't prove anything. Now, this is a good idea to work with things, especially when we don't know how to do this yet analytically. But how could I prove that the limit as x approaches 1 of h of x equals 3? Let me go ahead and fill this in here. Notice I use more, data points in the notes than I did here. And the more you use, probably the better off you are. You don't want to use like 2 points. That's not going to work because you don't necessarily see a trend. This might be trending towards 2.9. If you just use these points, it might be trending towards 2.98. And we don't know. So we try and get closer and closer and closer till we see an actual trend. But again, the question is, it appears to be that the numerical approach tells us that the limit is 3. How could we do that analytically, or how do we show that analytically? Well, me write the function down again. We got h of x equals x cubed minus 1 over x minus 1. How could I show this analytically? Well, we can manipulate functions to look different than what they are. And I'll give you an example of this. If I name a function as, let's say I've got 2x plus 3. Well, I could also say that f of x is equal to x plus 2 plus x plus 1. Aren't these equivalent functions? Yeah, they're the same function. X plus x is 2x, 2 plus 1 is 3. So what I did was I rewrote the function in a different way. Now in this case, why would we do that? I don't know. But could we rewrite this function in a different way so that it looks different but does the same thing or represents the same thing? Yeah. We can take this function and we can factor. We can factor this function down. We can factor the numerator and the denominator just to see if we see any trends. And so, let me go ahead and do that here. We factor this to say h of x is equal to, what was it, x minus 1 times x squared plus x plus 1. Okay, so x cubed minus 1 actually factors to that over x minus 1. Now some of you might be getting caught up in how to factor a trinomial. That's something that you learned in Math 3 in practice and analysis. I'm not going to spend a whole long time on factoring this down to this. This is basic stuff. You don't have to worry about it too much. Normally in calculus, the highest factoring we do is a quadratic, so an x squared. We might have an x cubed if there's a common factor, a GCF, but don't stress so much over that. You should know how to factor that, but don't stress over that. Anyways, these two functions are the same exact function. They are exactly the same in every single way because this simplifies to this. Now, what you might recognize is that the x minus 1, the factor here, reduces with the factor on the bottom. And so we might be tempted to say h of x equals x squared plus x plus 1. And in fact, this is not true. This function is not the same as this function because there's a problem here. There was a problem in this function. There's a problem at x equals 1. Okay? In this function, there is no problem at x equals 1. This is just a parabola. But these two functions are the same in every respect except for x equals 1, except for that factored portion, that factored piece. So h of x is not actually x squared plus x plus 1, but it is the same everywhere except at that point. Okay? And in fact, if you use your calculator to graph it, they would look exactly the same. The point is this: the limit as x approaches 1 of x cubed minus 1 over x minus 1 is the same as the limit as x approaches 1 of x squared plus x plus 1. These limits are the same because when we're finding a limit, we're not actually determining the value at that point. We are looking at values that are really, really, really close to that point. So our problem was x equals 1, but we're not actually looking at 1. We're looking at points that are very close to 1, all around 1. So these functions are the same everywhere, including really close to 1. So if I can evaluate this, that means this limit's going to be the same as that limit. And so here, because this function is continuous, all I have to do is plug in 1 to get an answer there. Okay, and so our answer there is 3. Okay, all right. Now I don't like, so like I said, we factored there, we simplified, but when we cross that out, we're now dealing with a different function than h of x, but the limit is going to be the same value. So these are not the same functions, but their limits are the same. Okay, so what's the idea? You substitute. If you substitute and you get an indeterminate form, then you have to do something else. But if you get an answer, you're done. If you get an indeterminate form, the first thing you try is factoring and then substituting. Okay, it's as simple as that. Let's take a look at another example here. we've got, oops, that is the same example. So we can conclude this exact point. We substitute and we end up with 3. So the limit as x approaches 1 of x cubed minus 1 over x minus 1 is 3. Okay. Now, let's go ahead and do a practice problem. So go ahead and pause the video and try this on your own. Remember to go through all the steps well. Do proper math. Don't skip steps. That would be a bad idea. Pause the video and then come back and see how you did. Okay, so remember our first step is always substitution. If we're going to skip that step, we're going to have a problem in the future. So never skip substitution. So I'm going to plug in 4. So 2 times 4 squared minus 5 times 4 minus 12 over 4 minus 4. Simplifying that, well, that's 16 times 2 is 32, minus 20 minus 12. Over on the bottom, we get 0. 32 minus 20 minus 12 is 0. So we got 0 over 0. That is not an answer. That is an indicator that the answer is something else. This is, what do we say? It's indeterminate. Indeterminate. And then from here, well, what do? We try factoring. What does 2x squared minus 5x minus 12 factor to? Well, we know one factor has to be 2x, and the other factor has to be x. And factors of 12 are 4 and 3. That's 4 and 3 won't work. 6 and 2 won't work. 12 and 1, no, what am I missing something here? 4 and 3, I believe. 4 and 3. 4, yeah. 4 here and 3 there. So that will give me 8x. So that has to be minus and a plus there. And then over x minus 4. So we are now looking for the limit as x approaches 4 of this guy. These are equivalent because we haven't reduced anything yet. We can see that the x minus 4 is reduced. And so this will be the same as the limit as x approaches 4 of 2x plus 3. And now we can just substitute. So we end up with 2 times 4 plus 3, which is 11. Okay? So again, you always check substitution first. You always check substitution first. If it gives you an answer, great, you're done. If it gives you indeterminate form, then you try factoring, see if you can reduce something, and then substitute after that. So it's pretty straightforward there. Okay? And again, just emphasizing that hint, use substitution method unless it results in indeterminate form. Now you see in the notes, 0 over 0 is indeterminate. Infinity over infinity is also indeterminate. We'll talk more about that in the future as well.